So welcome back to another day of Math 210, Calculus 1. So a couple things to talk about, just finishing up a few issues from section 5.1 that I also have videos about online, but it's good to make sure we acknowledge and talk about them. I'll talk briefly about section 5.2, which is a very short section. It's just introducing the idea of indefinite integration, which you should think of as just doing differentiation in reverse. And then later on, we will show how indefinite and definite integrals are related. But for just introducing the terminology, it's not that bad. And then I hope to put some time at the end of class to answer questions if you have them about the upcoming Chapter 4 test, which will be this Wednesday. Yeah, I guess I misspoke a little bit. It's actually a few things from 5.2, and then indefinite integrals is 5.3. Okay, so we stopped last time by figuring out that definite integrals are linear. And this time I'll just sort of state and go through a couple more properties, and then we'll do some exercises. So just by way of definition, we've been talking about this integral f of x dx from a to b. So this is the signed area under the curve. Typically our function f of x is assumed to be continuous, or even just piecewise continuous is fine. The integral will always exist. So this is the signed area. It's the limit of Riemann sums, and this number a has always been less than this number b. And just by convention, like if somebody gives you an integral from b to a with the bounds reversed, then I'm going to define this to be the negative of the integral from a to b. So you could think of it as saying something like maybe this was your function. It was piecewise continuous. It's partly a circle, then partly a line, and then call the area under the curve R the area above the curve S. So like if you're integrating from A to B, then that would be the signed area. It would be R minus S. If you're thinking about going from B to A, geometrically, what you should think about is you're kind of like reversing direction, reversing orientation. That's encapsulated by changing the sign. So you would use S minus R instead of R minus S. So if you were going from like B to A. But think of that just like a definition. And as a consequence of that, of course, if A is equal to B, then you would be doing the integral from A to A, f of x dx. And if you switch the bounds, you get a negative sign, right? And the only number that's equal to its own negative is 0, which also makes total sense, because if you are integrating a function, you want the area under the curve, but if you just go from A to A, then the area under the curve is just this length of the line. There's no area there. So the integral should be 0. The other thing we like to say let's go back to this picture and let's label these 3 points like A, B, and call that one C. So the integral from A to B of f is equal to r. That's the area under the curve. The area from, let's see, B, the integral from B to C, that's the signed area, so the negative of the area above the curve and below the axis. That would be equal to the negative of s. And the integral from A to B, we've already seen. That's signed area, that's r minus s. So that's like another way to write that is this is the integral from A to, or sorry, getting the bounds a little messed up. The integral from A to C going from here all the way to the end would be r minus s. And so and we've seen this is equal to integral going from A to B. That's r plus integral going from B to C. That's minus s. So this is called like additivity of domain. If you have a domain that you've now partitioned into 2 parts, then the integral from A to C would be equal to the integral of the first part plus the integral over the second part. And by the way, you can switch that around. So B doesn't even have to be between A and C. Like you could do something like what? So you could say integral from A to B of f of x dx is equal to integral from A to C f of x dx plus integral from C to B f of x dx. Like you can write stuff like this no matter what. And so how does that work out? Like A to B, that was this part, it was r. A to C was what? R minus s. And then C to B would be the negative of integral from B to C. So integral from C to B would be negative s, which would be plus s. So because of the fact that when you switch bounds, you pick up a negative sign, that makes it work out so that when you do this additivity of domain, you pick like 3 points, A, B, and C. Like, yeah, you can integrate from A to C, and that'll be equal to integral over this part plus that part. But it's also true that C doesn't even have to be in between like A and B, or like it's also true that C doesn't even have to be in between A and B, like we've got set up here. You just pick any number C as long as f is integrable over the whole domain. Integral from A to B will be like this part plus that part. And the way that it works is because when you switch the bounds to go back, it cancels out the right thing to give you like r on this side and r on that side. Yeah, there's a question of why is it s and not negative s? And so here's the calculation. So integral from C to B f of x dx is equal to, remember the bounds are opposite of what they should be. So this is equal to the negative of the integral from B to C. And the integral from B to C is the signed area. Integral from B to C is the signed area. It's the negative of the area under the curve. So the integral from c to b is actually just equal to this positive number s. Other questions or comments? And the other thing is pretty straightforward. It's this comparison theorem, which says that if you've got some function that's less than or equal to another one, on some interval, meaning for every x in that interval, f of x is less than or equal to g of x, then what you can say is that the integral from a to b of f of x is also less than or equal to the integral of g of x. So an inequality between functions will lead to an inequality of their signed area. And let's see if we can do a kind of like an illustrative example. So here's maybe my function f of x, and let's pick a function g of x that's always bigger or equal to. So f of x is definitely less than or equal to g of x at all times, and the signed area under the curve f of x is like this part minus that part, whereas the signed area for g of x automatically includes all of the positive part for f and perhaps some more stuff. And it's guaranteed to be subtracting away less than what you're subtracting away for the negative part. So you can see intuitively, I wrote equals when I should have written less than or equal. So you can see intuitively that the signed area of f of x is less than or equal to the signed area of g of x, just because the functions have the same inequality. But you can prove that analytically as well. Because if you compare any Riemann sum for like a Riemann sum for f of x to a corresponding sum for g of x, you'll get a similar inequality. The details can get a little bit technical, but let me do one just for right-hand endpoints. So remember, the right-hand endpoint approximation for f would be something like sum I goes from 1 to n, f of x I times delta x. And because f of x is less than or equal to g of x, this is going to be less than or equal to the sum of corresponding point for function g of x, right? Because f of xi is less than or equal to g of xi, f of xi times delta x must also be less than or equal to g of xi times delta x. And then you're just adding all those up, and the inequality stays the same. And so this one is the right-hand approximation for g. It gets a little bit more technical when you're allowed to choose sample points. But the result still remains true. And so the signed area, the limits, the signed area, the integrals are actually given by limits as n goes to infinity. So if two functions satisfy an inequality, one's less than or equal to the other one, then their limits will also satisfy that same inequality. which gives you that this integral is less than or equal to that one. I mean, let's take a moment and try to put it together. I mean, I'll show this one example. Like for how do you actually use this? So say you wanted to prove that 3/4 was less than or equal to this integral from 1/2 to 2 of 1 over x, which was less than or equal to 3. And I mean, later on in the course, we'll learn how to compute this integral with great accuracy, but for now, can we at least put bounds on it? And if you look at the graph of 1 over x, so this is, its derivative is negative, it's a decreasing function. So here we are at x equals 1/2, and here we are at x equals 2. And so the y value here would be 1/2, 2, and the points here would be x equals 2, y equals 1/2. And so if you want to use this comparison theorem, there's two natural ways to do it. You've got a lower bound given by 1/2, and you've got an upper bound given by 2. So you know that on this interval from from 1/2 to 2, you know that 1 over x is definitely less than or equal to 2, and you know that 1 over x is definitely bigger than or equal to 1/2. So given that you have those inequalities, you can take f of x equals 1 over x, you can take 2 equals g over x. And of course, this works the other way too. Like if you have a function like h of x that's less than or equal to f of x, then your integral of h of x would be less than or equal to the integral of f of x. It's just like a completely similar argument. So this is telling me that the integral of 2 is less than or equal to the integral of 1 over x, which is less than or equal to the integral of 3/4. But I know how to calculate the integral of a constant because that's just the area of the rectangle. So if I take integral of 1/2 to 2, so this is what's given to me by comparison theorem. The integral of 1/2 is less than or equal to integral of 1 over x. It's less than or equal to integral of 2. The integral of 1/2 is just base times height. It's 1/2 times 2 minus 1/2. So less than or equal to 2 times 2 minus 1/2. So that's telling me 2 minus 1/2 is 3/2. So this is 3/4 is less than or equal to integral of 1 over x dx, which is less than or equal to 2 times 3/2, which is 6/2, which is 3. And so we get that conclusion, and that's what we were asked to do, right? Yeah, that's what we were asked to do. And all that's saying geometrically is that the area under the curve is bigger than this rectangle, and it's less than that rectangle. And so geometrically, that's pretty clear, right? It's just this rectangle plus all that extra stuff. Or if you like, it's this bigger rectangle minus all that stuff. But analytically, what you're doing is you're representing that with this equation. So any question on that? So let me do one more example. This is kind of picking out a question from the chapter exercises that relates to this additivity of domain theorem. So if you're following along, this is number 62. And it says express each integral as a single integral. So in other words, given this integral from 2 to 9, f of x dx, of minus integral from 4 to 9, f of x dx. So can you express this as a single integral over a single domain? So you're using the fact that you can break up the domain. So I'll let you work on that for a few moments, and then I'll come back and show my answer too. Okay, so after giving you some time to work on this concept check, the way I would approach this is, well, I'm seeing 2 to 9 and I'm seeing 4 to 9. So I want to break up this first one as integral from 2 to 4 dx, and then plus integral from 4 to 9 f of x dx. And the reason why I want to do that is just because I saw 4 to 9 here. So I want to break this into pieces where it'll start to match. And now everything works out quite nicely because I'm going from 2 to 4, then from 4 to 9, and I'm subtracting that very same integral from 4 to 9, leaving me just with the integral from 2 to 4 f of x dx. So that's how you can play with the additivity of domain theorem to sometimes simplify your answers. Any final questions on any of that before we move on to next topic? Okay. So this is something we call anti-differentiation. And so we've done things like given y equals a function f of x, you know, like maybe f of x equals x squared. We've taken the derivative and found that the answer was 2x. You can also try to go the other way. You can say, given a function, can I find like a capital X, f of x, whose derivative is what I started with? So given y equals f of x, say that capital F is an antiderivative of little f if its derivative is equal to f. So for instance, I've just shown that x squared is an antiderivative of 2x. Lowercase f equals 2x, capital F equals x squared. But there are other antiderivatives of 2x as well. So if I had taken like x squared plus 2, the derivative is still equal to 2x. In fact, shifting the antiderivative by a constant will not change the function of which it's an antiderivative, because when you take that derivative, it just goes to 0. There are other ones. So like if I take f of x equal to 0, and I guess I should be like a little bit careful here. I should specify that I'm working on a fixed domain, so all my x's are in that interval from a to b. So you're an antiderivative on the domain from a to b. If that relationship holds for all x in the interval. So strictly speaking, you can be an antiderivative on some domain, but maybe not for a bigger domain. Okay, but in the domains I'm looking at here are just all real numbers. So, okay, so suppose your function is the 0 function, then there's lots of capital F's, like you could pick 2, you could pick any constant, then the derivative would be 0. If your little f was cosine x, your capital F could be sine of x. Your capital F could be sine of x plus 3 or sine of x plus any other constant. You're starting to see the pattern. Given a function, you find this whole collection of antiderivatives by just finding one, and then you can add a constant to it. It doesn't matter. So let's try to like formalize that. So here's this. So here comes this theorem. So it says that, say you've got some antiderivative. Right? So say that capital F is an antiderivative for lowercase f on some interval from a to b. So that's fine. And then I want to say that any other antiderivative has to be of the form capital F plus c. So then any other antiderivative has the form f of x plus a constant. So if you can find one antiderivative f, then every other antiderivative has to be that one plus a constant. And I can actually prove this for you. So let's say that I've got some other antiderivative, call it h. So the h prime of f is also equal to little f. That's what antiderivative means. When you take the derivative, you get back to what you started. And then what I want to do is simply look at the difference. I want to simply look at the difference between h and f. So h minus f of x. And I want to take its derivative. So I've got a function, I take its derivative, and that's equal to h prime minus f prime, which is equal to little f minus little f, because they're both antiderivatives of the same function, and that's equal to 0. But if you've got a function whose derivative is equal to 0 on an interval, say like on this interval from a to b, we know, we've proved with the mean value theorem, that if you are a function whose derivative is equal to 0 on an interval, then this function has to be equal to some constant c. Which, bringing f to the other side, tells you that h has to be f plus c. So the only possible way you could get two different antiderivatives of the same function is if they differ by a constant, or that is to say, if one of them is the other function plus a constant. So any questions or comments on that? So really, when we're searching for antiderivatives, we're looking for an entire collection. And we use this notation, which we call the indefinite. Integral. So if I say the indefinite integral of f of x dx, then what I mean by this is I want it to define this to be like the collection of all antiderivatives of f of x. So like all antiderivatives which you might colloquially write down as capital F of x plus c. So when it's just a single function, you call it an antiderivative. When you're thinking of it as the collection of all antiderivatives, you use this indefinite integral notation. It's kind of bizarre why you would use this notation right now, but it'll become clear when we do the fundamental theorem of calculus. You use this indefinite integral notation to like represent all of those antiderivatives, and you notate it just by saying, whatever function plus c. So for instance, just to give us some example practicing with this new notation, I could say something like indefinite integral of x is like x squared over 2 plus c, like that is to say, it's the collection of all functions of the form x over 2 plus a constant. Or indefinite integral of cosine x dx is equal to sine of x plus a constant. So to every differentiation rule, there is a corresponding integration rule, indefinite integration rule. So for instance, if I take the derivative of natural log of absolute value of x, so when x is bigger than 0, then f of x is natural log of x, and so f prime is 1 over x. When x is less than 0, f of x equals natural log of negative x, and so f prime is 1 over negative x, and then times the chain rule would tell us 1 over negative x times negative 1, which is 1 over x. So if f of x equals natural log of x, then evidently natural log absolute value of x for any x not equal to 0, evidently its derivative is 1 over x, and that's telling us that the indefinite integral of 1 over x dx is equal to natural log absolute value of x, and then you can add a constant to that. So like just as a for instance. Or you could look at, well, remember how we saw that the derivative of x to the n was equal to n times x to the n minus 1? So how would you do this in reverse? If I want to take the integral of x to the n dx, the indefinite integral, I need, excuse me, I need to find a function whose derivative is equal to x to the n. So finding a function that when I do this to it, the result is x to the n. And so what I'm thinking of is x to the n plus 1, because when I subtract 1, I want to get x to the n instead of n minus 1. And I want to divide by n plus 1, because when I take this derivative, out comes a constant n plus 1. I want it to cancel and just give me x to the n left over. And then like plus a constant of integration. So when you take the derivative, you'll get 0 plus, n times 1 over n times 1 times x to the n. You'll just get back this x to the n. So that gives us a nice little integration formula there. So all these little integration formulas are going to start popping up, but don't be confused. Just get used to the notation. It's just saying that the derivative of the right-hand side is equal to the integrand. That's all it's saying. Nothing else beyond that. And similarly, because derivatives are linear, indefinite integrals will also be linear. So that is to say, if you want to take, like if I give you this problem, if I tell you to find the integral of cosine plus sine, then one way you can work this out is by separately looking at integral of cosine x and then integral of sine of x. And it might be easier to work these out separately because any derivative of cosine the sine of x plus a constant, any derivative of cosine is, of sine, excuse me, is negative cosine of x plus a constant. And instead of adding like two different constants, just sort of roll them up into one and put it at the end. It's usually what we do. Because if the constants are arbitrary anyway, like why would you introduce like c and d or whatever? Just say like there's one constant at the end. And the derivative of something, the derivative of an expression like this will of course be equal to cosine plus sine of x. So that's how you use what we call like a linearity property of the indefinite integral. By taking something that's like a sum or multiplied by a constant, you can break that up. You can pull the constants out to the outside of the integram. There's a question of like, where does this n plus 1 come from in the formula? To explain that again, so like what if n was equal to 3, then what's the antiderivative of x cubed? So I think that should be x to the 4th over 4 plus a constant. So this should help you see where the n plus 1 comes from, because if you take the derivative x to the 4th over 4 plus c, you're going to get, by the power rule, 4x cubed over 4, and then derivative of constant is equal to 0. So for general x to the n, it has to be x to the n plus 1 over n plus 1, because when you're differentiating, you'll move down that exponent and subtract 1 from that exponent. So that's where it comes from. And so, yeah, really from every single differentiation rule we've done so far, there comes a corresponding integration rule. You can see the other ones for like the 6 trigonometric functions. There's a little table on 313, but I won't like go through every single one. And there's also these involving e to the x. So integral of e to the x is e to the x plus c. Integral of e to the k times x equals 1 over k times e to the k x plus c. It's kind of no big deal. They're the opposites of the differentiation rules that we've seen. Okay, so like with about 10 minutes left, I know that's not a ton of time, but take a moment. Any questions or concerns you have for tests, anything you want me to answer? Take a moment, collect your thoughts, and you can ask me or you can private message me, whatever you want to do. Okay, seeing no questions at the moment, I'll hang out for 7 more minutes, but I'll go ahead and stop the recording and just let you know we're having a test this Wednesday. Get in contact with me, any questions, concerns, so on and so forth, and otherwise I'll see you then. I'll stop the recording now.